introduction. Good morning, everyone. So let me start with a brief recap of what we finished with yesterday. So if you remember, yesterday we were discussing the gluing step of the inductive construction of the universal cover of the counterexample to the Miller conjecture. So this is the step where we started from two copies of the manifold Mi bar obtained at the previous step of the induction, and we try to extend it to a new manifold, larger manifold Mi plus 1, in order to be able to extend the group action of gamma I to a group action of gamma I plus 1. Okay, and this inductive step worked in the following way. So we pick two copies of the previous manifold, Mi, okay, and we add on top of them a new copy of a free sphere times a 4 disk. Okay, now then we removed two copies of a small 4 disk from the big 4 disk. Okay, and in this way we obtain a new manifold with three boundary components. Okay, the exterior boundary component, that one was the boundary component that we would like to keep for the next step. Okay, and then we killed the interior boundary components by gluing into them the boundaries of the two copies of the manifolds obtained at the previous steps. Okay, and the crux of the argument was that in order for the extended action of the group capital gamma I plus 1 to make sense, we wanted the gluing maps, so the diffeomorphism from the boundaries of the old guys, which are diffeomorphic to S3 times S3, to the two interior boundary components of the new guy, which are still diffeomorphic to S3 times S3. Okay, so we would like this diffeomorphism to conjugate the op function with speed 1 on the first factor and k on the second factor to the op function with speed 1 on the first factor and 0 on the second factor. Okay, so today I'm going to discuss some of the ideas that get into the construction of the smooth invariant metric with the non-negative Ricci curvature on this guy. Okay, and as I anticipated yesterday, okay, so the main challenge for this step is going to be that the diffeus phi I1 or 2 cannot be chosen isometric with respect to product of round metrics times S3. Okay, so before I move to that, so let me stress that for today the focus will be on one single step. So we will forget about I. Okay, we will set today I is fixed. So I'm gonna call P phi what I called phi I yesterday. Okay, and also I'm gonna set k. What here I call so here k was 2 to the I minus 1. I'm sorry. Okay, so I'm gonna set k equal to 2 to the I minus 1. Okay, it doesn't really matter, so we are able to do the construction for every k. Okay, so I just do it on a generic k. Okay, so let me spend a few minutes by stressing that. So this is the main challenge, but this is not the only challenge. Okay, so let me put it as an exercise. So imagine that you can find a metric such that the glue diffeomorphism phi is an isometry between boundary components. Imagine that phi is an isometry between the boundary components. Okay, then the gluing admits a C0 Riemannian metric okay, defined, so if you have a Riemannian metric here and a Riemannian metric here and the gluing map is an isometry, then you can define a C0 Riemannian metric on the glued guy by letting it be the original Riemannian metric here and the original Riemannian metric here. Okay, however, the point that I want to stress is that even to the metric here has non-negative Ricci curvature and the metric here has, say it has positive Ricci curvature here and the other metric here has positive Ricci curvature. Okay, it is not clear that you can, let's say, smooth out the C0 Riemannian metric that you get here to a metric with non-negative or positive Ricci curvature on the result of the gluing. Okay, so even to, however, even say globally. Okay, let me convince you of this fact with some examples. Okay, so imagine that, so let's discuss a toy model. Imagine that you start from the round sphere. So this is S2, G round. Okay, with constant sectional, constant Ricci curvature equal to 1. In particular, Ricci curvature is greater or equal than 1. Okay, now I pick another copy of this guy. Okay, now I remove two small geodesic balls with the same radius. Okay, so now the, let's call it the identity map, is clearly an isometry between the two boundary components, so I can stick them together. Okay, however, so if you want to get a metric, so the result as a manifold is the connected sum of these two guys, which is a sphere, which clearly admits a metric with with Gaussian curvature, Ricci curvature greater or equal to 1. However, if you want to really get such a metric by perturbing the C0 Riemannian metric that you get here, okay, this is not possible with a local perturbation. This is clearly suggested by the picture. You need to do something more global in order to get back a metric with Ricci curvature greater or equal to 1 on this guy. So you cannot just do something like this. Okay, this is gonna get some negative. Okay, so here there is some obstruction to a local deformation, but the point that I'd like to make is that there might be topological obstructions which are more of a global nature. Indeed, this is illustrated by this example. So pick a gamma, a subgroup of S4, gamma different from the identity, acting freely on X3. Okay, and consider the spherical space form S3 of gamma with phi1 isomorphic to gamma. Okay, now, so this is a round metric. You can choose a small geodesic ball. Okay, you can try to get the metric with positive Ricci curvature on the connected sum of this guy with itself. Okay. However, the claim is that so clearly there is an isometry between the two boundaries of the geodesic balls that you remove. Okay. However, the claim is that there is no metric with Ricci bigger than 0 on the connected sum of two copies of this guy. Okay, and this I'll give you as an exercise to check. So there might be more structure, more global obstructions. Okay, so challenge. The second challenge is really a challenge. Okay, however, I will ignore it. Okay, so there are other challenges, but I will ignore them. Okay, any questions? Okay, so the idea is that we would like to realize this gluing through a gluing neck. Okay, this gluing neck is going to be diffeomorphic to S3 times S3 times 0, 1. Okay, this is what yesterday I called sometimes a collar. Okay, if you think about it, so you need such a collar also for making rigorous the statement that yesterday I took for granted, that if you glue these two guys with the diffeomorphism between the boundaries, then you get a smooth structure on the result of the gluing. So you need to introduce such a gluing neck even for making careful the fact that the manifold that you obtain by sticking together the pieces has a smooth structure. Okay, and the picture that we should have in mind for this gluing neck is the following. So okay, so these are going to be the time slices. Say there is going to be a time parameter t going in 0, 1. These are going to be the time slices. They are all diffeomorphic to S3 times S3. Okay, so here maybe. Okay, this is the picture of the gluing neck that we see starting from this boundary component, starting from the previous component. Okay, where as I told you yesterday, what you see is a rotation with speed 1 here and speed k here. So the action is rotating k times faster on the second component than it is rotating on the first component. Okay, and then what we would like to do is a change of coordinates. Okay, and so this neck is going to have a different set of coordinates. Okay, and this change of coordinates respects the time slices. Okay, and it is induced by the diffeomorphism phi that I introduced above. Okay, and the tricky thing is that with respect to this new set of coordinates, okay, the action that you see is pretty different. Okay, you see a rotation with speed 1 on the first component and nothing on the second component. Okay, now I would like to endow the neck with a metric of the form G equals dt squared plus some rescaling function that I'm going to call f times a family of metrics gt. Okay, so this is a family of matrix on S3 times S3. Okay, so these are the metrics on these time slices. Okay, and I would like this family of metrics. So this is a family of metrics parameterized by 0, 1. Okay, and I would like this family of metrics to satisfy the following properties. So I would like G0 to be a product of round metrics. I would like GT to be invariant with respect to the 1K of circle action for every T. Okay, then I would like G1 to be the fullback with respect to the diffeomorphism phi of the metric G0. Okay, and let me stress that the diffeomorphism phi is the one conjugating the two actions. So theta 1, 0 composition with phi should be equal to phi composition with theta 1 k. Okay, and lastly, I would like the Ricci curvature of GT to be positive for all times. Okay, so there was no metric here in the picture. Let me draw a picture which is more respecting the choice of this family of metrics. Okay, so what's going to happen is something like this. Okay, so if you stare at the neck with the identity chart, but
they want the Ricci of GT or Ricci of G to be.
I'm going to comment on that in a few minutes. Okay, so if you stare at the neck as a Riemannian manifold through the chart which is suggested to you by this guy, okay, the picture that you see is the following. So you have a family of metrics on the slices. You start from the product of two round metrics. However, a step at a time, the metric becomes really strange. Okay, and then, okay, if you look at the net through the lens of this diffeomorphism, then what happens is that on the top, the metric becomes the product of two round metrics. Okay, and since the diffeomorphism, so I told you that the diffeomorphism cannot be the identity, and indeed the diffeomorphism is going to be really strange, let's say. Okay, what happens is that the original metric here, which looks like a product of two round metrics, is going to become really strange with respect to the new chart. Okay, so this is the product metric, and the diffeomorphism is doing two things. It's doing this metric stuff, okay, it's also conjugating the actions as well. Okay, and if you're able to build such a net, then you are almost done. Okay, and what are the reasons? Let me comment on the choice of these conditions. So first, a sloppy remark. So why do I choose the product of round metrics here? So we all like round metrics, and the naive remark is that if you choose a different metric here, the difficulty will be just hidden in another step of the construction. So it wouldn't change much. Okay, so why do I want condition 2? So condition 2 is not needed, but it is really helpful because it guarantees that every metric of the form dt square plus f of t square gt is invariant under the 1K action. Okay, condition 3 is my compatibility condition that I was looking for. So with this choice of the metric, the diffeomorphism phi conjugates the actions, but now it becomes an isometry between the boundary components. Okay, 3 is a compatibility condition. Okay, and 4 gives me a lot of flexibility, okay, to endow the net with the metric with non-negative Ricci curvature. Okay, so the disclaimer, so I'm not claiming that all these conditions are necessary. Okay, this is just how the construction works. Okay, let me finish this part with an exercise. Okay, so if you go back to the toy model where S3 times S3 was replaced by S1 times S1 yesterday. Okay, so okay, the exercise asks to find an analogous family of metrics which, instead of being positively Ricci curved, are flat. Okay, any questions?
Question. So far you still have not defined what the diffeomorphism is, right?
This is what I'm going to do now.
So actually part of this, the job of finding this matrix is also to find the diffeomorphism.
Exactly. Yeah. Yeah. Any more?
On the induction step, do we
Yeah.
already have the metric on MI?
So this is a point on which I've been sloping. So let's say that the metric on this collar of MI, okay, looks very close to a product of the standard round metric on S3 and the flat metric on the disk. Okay, and what I really care about is that the induced metric on the boundary is a product of round metrics. Okay, so and the inductive step is meant to keep this form of the metric at the end of the green construction. Okay. Anyone?
And the metric on the S3 times D4 that we glue MIs in is just the standard metric.
Exactly. You can think that it is a standard metric. Okay, so let me start the discussion about the existence of the diffeomorphism by reminding you of a classical theorem in Riemannian geometry. So the theorem says the following. So let G be a compact, say, D group acting isometrically and freely on a Riemannian manifold MG say on the left. Okay, then the orbit space G, M mod G can be endowed with a unique smooth structure such that the natural projection to the orbit space and the Riemannian metric G on G mod M, such that the natural projection to the orbit space from M to M mod G is a Riemannian submersion. Okay, and moreover, this turns G goes into M mod G into a principal G bundle, and the induced metric on the orbit space the induced distance is the orbit distance. Okay, so we are going to use this a few times in the rest of the lecture. So let's start from the following observation. So if there is phi from S3 times S3 is itself conjugating the two actions, then we'd better the quotient spaces to be diffeomorphic. Okay, so you can apply, so I told you yesterday that the 1K action and the 1,0 action are isometric with respect to products of round metrics. Okay, we can apply the theorem, okay, and get a smooth structure on the quotient spaces. So let me put it this way. So okay, so the quotient of S3 times S3 modulo the 1K action should be diffeomorphic to the quotient of S3 times S3 modulo the 1,0 action. Okay, however, so if you solve the exercise so that I gave you yesterday, you know that this is only acting on the first factor. Okay, so this is the quotient of the free sphere modulo the op function. Okay, and this is S2. So we know what the right hand side is. Okay, and the starting point is going to be to check that these two guys are indeed diffeomorphic. Okay, so this is not our discovery, it has been known for a long while. There is a paper of Gromov going back to several years ago, where he says that the fact that these two manifolds are diffeomorphic is an accident. Okay, and for today, we are going to call it a miracle. Okay, not an accident. Okay, let's see how this miracle, where this miracle comes from. Okay, so recall. So S3, the free sphere, is the underlying smooth manifold of a Lie group. Okay, so the underlying smooth manifold of and I'm gonna identify the two for the rest of today's lecture. So with this identification, we can view the op function as a multiplication in SU2 of the term. So what I yesterday called theta times g. Okay, so this is an element of S3, which now I'm going to view as an element of SU2, and this was the op rotational angle. Okay, this is equal to e to the 2 pi I theta 0 0 e to the minus 2 pi I theta times the matrix in SU2 I'm identifying little g with. Okay. Any questions? Okay, so now there is. Am I viewing the op function on each component of S3 times S3 as a left action? Okay, there is a commuting, so there is a right SU2 action on S3 times S3, but by right multiplication on the second component. Okay, so here I'm defining an action at SU2 on S3 times S3, and I'm viewing S3 and S3 as SU2 as well. Okay, so I pick little g here, little g1 here, little g2 here, okay, and they go into little g1, little g2 multiplied by little g on the right. Okay, and the remark is that the S1 1k action on S3 times S3 on the left, okay, where you multiply by this matrix the first component and by the same matrix with kappa here to multiply on the left, okay, and the right SU2 action that I just defined commute. Okay, this is obvious. Okay, on one end I'm doing multiplications on the left, on the other end I'm doing multiplications on the right. Okay, and it's clear that they do commute. Okay, and they are both isometric. With respect to the product of round matrix. Okay, so now I can apply the theorem to the first action. Okay, I get the smooth Riemannian metric on the quotient space. Okay, and since the two actions commuted and isometric, this means that there is an induced SU2 right isometric action on this quotient space S1 1k, endowed with a quotient metric. Okay, let me call it H0. Okay, so this is a quotient metric of the product of round metrics that I call G0 with respect to this isometric action that I get by applying this theorem that I wrote over here. Okay, so now the thing which requires a justification, okay, and I'll leave you as an exercise, is that this SU2 action. So clearly the right SU2 action that I defined here, okay, is free. Okay, it's just the multiplication inside the Lie group. Okay, the exercise asks you to check that also the induced action is free. Okay?
From the equation, how do we get the left action? G1 remains G1, right? On the right hand side, we are multiplying with G2.
So the first component is it remains the first component.
Yeah.
The second component is multiplied on the right by the element of the group.
Yeah. So how do we get the action of S11K on from the left? How do we get the left action?
So it's I multiply G1, G2. Okay, G1 I multiply by this matrix.
I see.
Okay, and G2 I multiply on the left. Okay, and G2 I multiply on the left by this matrix where I put the kappa here. That's the answer? Okay, so now I have a free and isometric action of a compact Lie group on a smooth Riemannian manifold. Okay, and apply the theorem once more. And the theorem implies that SU2 goes into S1 1K mod S3 times S3 goes into the quotient, which is S2, as I'm going to check in a minute. Okay, this is a principal SU2 bundle. Okay, why is the quotient space S2? Okay, and the reason is the following. So I'm taking the quotient of S1 1K. So I divide S3 times S3 by S1 1K, and then I'm taking the quotient with respect to S3, which is isomorphic, which is the underlying. So I'm identifying, as I said, S3 with this SU2. Okay, so I told you that the two actions commute. Okay, so this is equal to S1 1K modulo S3 times S3 modulo S3. Okay, now however, so if you quotient S3 times S3 modulo the first action, okay, then what's going to happen is that you are killing the second factor. Okay, so this is equal to S1 1K modulo S3. Okay, however, now S1 1K is rotating by speed 1 on the first component and by speed k on the second component. There is no second component anymore. So this is S1 of modulo S3. Okay, and if you did the exercise, you know that this is isomorphic to S2. Okay, now, okay, remember our goal was to prove, one of our goals is to prove that this space is diffeomorphic to S3 times S2 times S3. Okay? Now I can call into play a proposition. Okay, which says that principal G bundles over a sphere Sn are in bijection with phi n-1 of G. Okay, so for us, n is equal to 2, G is SU2, whose underlying space is S3. Okay, so principal S3 bundles over S2, like this one, are in bijection with the pi 1 of the group, which is trivial. Okay, so this implies that this bundle is isomorphic to the trivial bundle, okay, which is the product of S2 with S3. Okay, and what does this mean? Okay, this means that if I call n, so I already called it n, no? Okay, let me call this n. Okay, this means that, so okay, so this is the bundle projection. Let me call it pi tilde 1k. Okay, so this is the bundle projection of the trivial S3 bundle over S2, which is just the projection on the first component. Let me call it pi 1. Okay, the two bundles being isomorphic means that there exists an isomorphism, a diffeomorphism, pi tilde, between this guy and this guy, which is equivariant with respect to the S3 action on N and S3. Okay, so phi tilde is equivariant, is SU2 equivariant differ between N and S2 times S3. Any questions?
So you're saying that SU2 is simply connected?
SU2 is simply connected because the underlying the underlying smooth manifold is diffeomorphic to S3, which is simply connected. Okay? Any more questions? Okay, so what happens now? So remember, we would like to find our diffeomorphism phi. Okay, and the diffeomorphism phi should in particular fill in this diagram. Okay, so let me call pi 1k the projection onto the orbit space with respect to the 1k action. Okay, let me call pi, I don't know, pi 10. Yeah, pi 10 is a good choice. So the projection onto the orbit space with respect to the 10 action. Okay, which, as I said, is quotient with the first factor and giving you S2 times S3. Okay, so the diffeomorphism that we would like to find, so we would like to find an S1 equivariant differ phi from S3 times S3 into itself. Okay, conjugating so such that the diagram commutes. Okay, so now let's look at the composition of this map with the inverse of this map. Okay, now I'm getting two principal S1 bundles. Okay, so I get S3 times S3 phi 1k n S3 times S3. Okay, those are principal S1 bundles over n, which is diffeomorphic to S2 times S3. Okay, if I rephrase what I would like to get, what I would like to prove is that these two principal circle bundles are isomorphic. Okay, now I can call into play another classical statement. Okay, so principal S1 bundle over n are in bijection with the elements of the 2 cohomology of n with integer coefficients. Okay, so this is the 2 cohomology with integer coefficients of S2 times S3. Okay, and therefore this is isomorphic to Z. Okay, and how do I check that the two bundles are associated to the same element? Okay, they are, because if you pick different elements, modulo the choice of the orientation, okay, you get different fundamental groups on the total spaces. Okay, so the total spaces are simply connected. Okay, and this means that the two bundles are isomorphic, which implies that our differ phi from S3 times S3 in itself exists. Any questions?
May you again clarify the strategy of the proof of the existence, because we already get that these bundles SC2 blah 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 and S2 times S3 are isomorphic.
Yeah.
Then we have this phi tilde.
Yeah.
And why it is not F what we want phi? What is the reason to from phi tilde to phi?
Because I wanted, so if you remember, I wanted the phi from S3 times S3 into itself, such that theta 1, 0 composition with phi is equal to phi composition with theta 1k. Okay, for the moment, if you forget about what I wrote after this line, okay, you only found phi tilde between the quotient spaces. Okay?
Okay.
Does it clarify? Any more questions?
After the H2N thing, you said something about different fundamental groups. Or
Yeah, so you need to check. So the proposition tells you that to any circle bundle, principal circle bundle over n, okay, you can associate uniquely an element of H2 of n with Z coefficients. Okay, so now I need to tell you that these two principal circle bundles are associated to the same element. Okay, why is it the case? Okay, if you pick different elements, the total spaces, which are diffeomorphic, would have different fundamental groups. Okay, so if you pick one, so there is the trivial one, which is S1 times n, okay, where you just rotate on the first component, okay, and this is associated to 0. Okay, now there is our guy, which is associated to 1 or minus 1. Okay, if you pick another guy, so if you pick 2 here, you would get the total space with I1 isomorphic to Z mod to Z. Okay, but the total spaces do not have fundamental group. Okay, and this is telling you that you need to pick a so-called primitive element inside Z. Okay, which is unique up to the orientation. Any more questions?
Why do you call it a miracle?
Because in principle there is no reason why it should be true. So there is no abstract reason why. So if you pick maybe another manifold with two circle actions and you try to prove that they are they are conjugated, probably they are not. Okay.
The construction, so it's very abstract.
Yeah.
And you don't need to be more precise.
So
you don't read in order to construct the measure.
it's not. You don't need more. So when it comes to constructing the metric, you need to be. You need to make a few choices. Okay. But the starting point is this one. You don't need more about the conjugating diffeomorphy. And let me also note that so you can find the formula for the conjugated diffeomorphism. Okay, it's explicit, it's not nice. But so if you start from the formula, it's not so clear how to find the family of metrics. Well, this construction, this abstract construction of the diffeomorphism phi is already giving you some hints about so concerning how to construct the family of metrics. Okay, I'll spend the last 10 minutes to give you a very sketchy idea of how that works. So I found the diffeomorphism phi, okay, and I want condition 3 in my list to be satisfied. So I should set G1 to be the pullback of G0 with respect to phi. Okay, so note that with this choice, the unique H1 on N such that phi 1k from from S3 times S3 with G1 to N with H1 is the Riemannian submersion. Is the pullback, so you look at the diagram above there, so you can easily check that the unique such metric is phi is the pullback of G_S2 of radius 1/2 plus G_S3 of radius 1. Okay, so say that G0 is a product of two round metrics with the radius of 1. Okay, so this you can easily check by staring at the diagram. Okay, so now H0, so G0, H0, and G1, H1 turn this guy, so S1 goes into S3 times S3, GI goes into, so let me do it this way. So I look at S3 times S3 GI. I take the projection with respect to the 1k action, and I get into NHI. Okay, and then I take the second projection with respect, taking the quotient with respect to the S3 action. Okay, and I get to S2 G S2 1i. Okay, so these are both principal G bundles, where G is S1 here, and G is SU2 here. Okay, they are Riemannian principal G bundles for I equal to 1 and to 2. Okay, and I claim that we can find GT and HT such that, so this is true for every time now. Okay, so S3 times S3 and GT. Okay, so it might seem that I'm making the problem more difficult. Okay, so I wanted to find the family G of T. Now I want to find two families of matrix GT and H of T. Okay, why is it useful? Okay, the reason is that the construction works backwards. Okay. And I would like them to have both positive Ricci curvature. Okay, so first I would like to construct the matrix H of T, okay, and then I would like to construct the matrix G of T using the matrix H of T. Okay, and why is this possible? Okay, this follows by understanding well the proof of two classical theorems. So the first one is a theorem due to Nash in 76 and also Pour around the same years and Berard and Julie. Okay, which says the following. So let G goes to M mod G be a principal G bundle with G compact and semi-simple. Okay, if you don't know what semi-simple means, what's important for us is that SU2 is semi-simple. Okay, if M mod G admits a metric G M mod G with strictly positive Ricci curvature, so Ricci greater or equal than C bigger than 0, then there is a G invariant metric G on M with Ricci greater or equal than C over 2, such that the projection from M G to M mod G, G M mod G is a Riemannian subtension. Okay, so you know that the metric H0 and the metric H1 are both obtained applying this theorem, okay, with a metric on the base, which is the round metric on S1 or on S2. Okay, and if you understand the proof of this theorem, okay, you're going to see that there is enough flexibility in order to be able to interpolate between H0 and H1 with a family of metrics with the same properties for all times. Okay, now you got the family H of T, you go one step up, and you apply another theorem. So you look at the proof of another theorem, which is due to Gilchrist, Arp, and Tushman in 98. Okay, which says the following: let y, g, y, f be compact with positive Ricci. Okay, and consider the principal F1 bundle S1 goes to M goes to Y. Okay, then M admits an S1 invariant metric with Ricci bigger than 0 such that the projection from M to Y is a Riemannian submersion. If and only if phi 1 of the total space is finite. Okay? So one direction is trivial. Okay? This follows from the very first theorem that I stated in the first lecture. So if you have a metric with positive Ricci curvature, you don't care about invariance. This is going to tell you that the fundamental group is finite. The other direction is non-trivial. Okay? And this is what we need. Okay, so note that the total spaces here are simply connected. Okay, we have matrix G0 and G1, which are obtained by applying this theorem. Okay, and I claim that if you look carefully at the proof, okay, you will understand that you can interpolate between G0 and G1 with a family of matrices which all satisfy those problems. Okay, and I'll stop here. Thank you for the time.